Hello everyone. So in the last video we learned about linear equations, what a system of linear equations is. We saw an example with a system with two equations and two variables, and we showed how to solve it using just plugging in with the equations. And we saw what it means geometrically for a system of two linear equations with two variables to have a solution, which is an intersection. Okay. Well, now today in this video I'm going to show you how to solve a system of linear equations. How to solve a system of linear equations by using something called a matrix and using what we call elementary row operations. We'll see that in a second. So let's begin. Okay. So in the last lecture, I remember we ended with the following theorem. Any system of linear equations has either zero solutions, one solution, or infinitely many solutions. And we saw for two dimensions where you have two lines, if you have a line here and let's say a line here, then the intersection is the solution of this system of two linear equations in two dimensions. So we would have two variables, right? So two lines in two dimensions can either have one intersection, it can have zero intersections, or if the lines were on top of each other, and here's the other line, then you see this is infinitely many solutions. So one solution, zero solutions, infinitely many. So this was when we had two equations, two variables. Okay? We will see an example of what it means geometrically to have infinitely many solutions or zero solutions or one solution for a 3D example where we have three equations and three variables. We'll see an example of that a little bit later. But the idea is that this theorem works for any system of linear equations, whether it's three equations, two variables, three equations, 2 million equations, 5 million variables, right? And you may ask, oh, that's ridiculous. Why would we have such a system of linear equations? Well, actually, systems of linear equations that are very large like that have applications in engineering and economics. And we'll see examples of that too in the book as we continue. So let's look at an example. Let's look at the following example. First, let me introduce, this word notation, it just means how we represent our mathematics using symbols. So for example, if I had y equals f of x, y prime equals f prime of x. Well, this is the same thing as dy dx equals d dx of f of x. Okay? This is the same. The meaning is the same. The only difference is the notation, which is the symbols that we use. Okay? Okay, so let's say we had the following system of linear equations, where we have x1 minus 2x2 plus x3 equals 0. And then we also had 2x2 minus 8x3 equals 8. And we also had 5x1 minus 5x3 equals 10. If you wanted to solve this system of linear equations, if you wanted to find a solution, the solution would look like this: x1 equals, x2 equals, and x3 equals. Well, if we wanted to find a solution, you can do what we did for the 2 dimensions, where you say 5x1 equals 10 minus or 10 plus 5x3, x1 equals 2 plus x3 because we divide by 5, and then we take this and we plug it in here and solve for x2, and then we take that and we plug it in here, okay, and then maybe we will get an answer. But this method here is too long. It will take way too long to solve this system of equations using this method here. So we're going to develop a new method to solve this system of equations using what's going to be called a matrix. Okay. So we can take this system of linear equations and make a matrix. So we just make a matrix where we put x1, x2, and x3, the coefficients, into the columns of this matrix, and then we put whatever the answer is, we put it into this column. So what's in front of x1 here? I have what's in front of x1 is a 1. And what's in front of x2 is negative 2. So I put negative 2 here. What's in front of x3 is 1. So I put a 1 here. And it equals 0. So I put my 0 here. And then here, in this equation, I have 0 in front of x1 because I have 0x1 plus 2x2 dot dot dot. So I'll have a 0 for x1. I'll have a 2 for x2, negative 8 for x3, and 8 here. And then I will have 5, 0, negative 5, 10. Okay. This is called an augmented matrix. And it represents this system of linear equations. If I had a matrix that looks like this, 5, 0, negative 5, without this part, then this right here is called the coefficient matrix. If I have an equation 2x plus 3y equals 5, 2 and 3 are called coefficients. Okay. Okay. So now I want to find a way to solve this system of linear equations, to find the solution for this system using this augmented matrix. Okay? Well, before I can do that, I have to tell you how I can change this augmented matrix into another augmented matrix so that it gives me the solution. Okay? But you may ask, okay, how do we change it? And how do we know that this will give us the solution? Well, I have to give you rules on what you can do to change this augmented matrix so that you do not change the solution of the system of linear equations. Okay? And how do you do this step right here? Through what we call elementary row operations. Let me show you what elementary row operations are, and then we will use them to solve this system of linear equations. Okay? We will use elementary row operations to change this augmented matrix into a different augmented matrix, which will give us the solution. Okay? For example, if I had 1, 0, 0 here, and I had 3 here, then this would tell me that x1 plus 0x2 plus 0x3 equals 3. So this would tell me that x1 equals 3. So I would just need x2 and x3, and that's my solution. Okay? So now let me give you elementary row operations and then show you how to use elementary row operations to change the augmented matrix into an augmented matrix which gives us solutions. There are 3 elementary row operations. One is called replacement. Okay. Replacement means that you can take any row and replace it with any other row. So for example, I can go like this. I can switch these two and say this is 0 to negative 8, 8, 1, negative 2, 1, 0, 5, 0, negative 5, 10. Okay. What did I do here to go from here to here? I used replacement, and I just replaced row 1 with row 2. Okay? Why would we do something like this? I'll show you why. But for now, let's just understand what these elementary row operations are and how we do them. And then I will show you how elementary row operations will help you find a solution. Okay? The second elementary row operation is called interchanging. So actually, what interchanging is this right here. We can interchange this row with this row. Okay? This is what interchanging is actually. Okay? What replacement is I can do this. I can take any row let's say row 5, row 3, and I want to replace row 3 with row 3 minus 5 times row 1. This is called replacement. Okay? And what replacement is I can multiply any row by a number, and then I can add it or subtract it to any other row. And that's called replacement. And again, I will show you how this will help us solve the equation, but for now I just need you to know that this is replacement right here, and we can do replacement and it will not change the solution of my system. And we could also do interchanging. Interchanging is this. Let's say row 1, switch it with row 2. Okay? This is called interchanging. And 3 is called scaling. Scaling a row means that I could just multiply that row by any number. So for example, I can say, I can multiply row 1. I could replace row, let's say row 3, by 1 over 5 row 3 here. When I do that, the matrix I will get is 1, negative 2, 1, 0, 0, 2, negative 8, 8, and then 5 divided by 5, 0 divided by 5, negative 5 divided by 5, and 10 divided by 5, because that's the row operation that I want to use. So if I did that, I will get 1, 0, negative 1, 2. Okay? This is called scaling. Now, elementary row operations are important because when I do elementary row operations, I do not change the solution of my system. So these do not change the solution of the system. Okay, so now I'm going to show you, I'm going to use elementary row operations to change this matrix into a matrix that gives us a solution. And then later, I will show you a set of rules that will, every time, will find a solution using elementary row operations. Okay, so let's look at this example here, and let's see if we can use elementary row operations to find the solution for this system of linear equations. Okay. So we have 1, negative 2, 1, 0. We have 0, 2, negative 8, 8, 5, 0, negative 5, 10. Right? Now, here's what I want to do. What I want to do is I want to keep the very first row in the first column, I want to keep that as a 1. Okay? And then everything below it, I want to make it a 0. Okay? So let me do that. I will take row 3, and I will replace row 3 with row 3 minus 5 row 1. And when I do that, I get 1, negative 2, 1, 0. I get 0, 2, negative 8, 8. And then I do 5 minus 5 times 1. So 5 minus 5 times 1 is 0. And then I will do 0 minus 5 times negative 2. So 0 minus 5 times negative 2, which is going to be 10. And then I'll do negative 5 minus 5 times 1. So negative 5 minus 5 times 1, which is negative 10. Okay. So I have 0, 10, negative 10. And then I will do 10 minus 5 times 0, which is just 10. So here, for row 3, I have 0, 10, negative 10, 10. And now what I want to do is I want to scale row 2 and row 3. So I will replace row 2 with 1 over 2 row 2. And I will replace row 3 with 1 over 10 row 3. And when I do that, the matrix I get, row 1 I haven't done anything to. Row 2 is 0. What's 2 divided by 2? I'll get 1. Negative 8 divided by 2 is negative 4. 8 divided by 2 is 4. And then row 3 I divide by 10. 0 divided by 10 is 0. 10 divided by 10 is 1. Negative 10 divided by 10 is negative 1. And 10 divided by 10 is 1. Okay. So the first thing I wanted to do is I wanted to get this to be a 1, this to be a 0, and I wanted this to be a 0. And we see here we have that. So the next thing I would want is I go to row 2 and I choose the very first number that is not a 0. So this one is a 0. This one here. So I have this one here, right? And everything below this, I should make it a 0, just like I did here. I made this one a 0, I made this one a 0. So then I choose this, and since it's already 1, that's okay. But what I want to do now is below it, I want to make this a 0. Okay? So let's do that. So to do that, I take row 3 and I replace it with row 3 minus row 2, because I'll have 1 minus 1, which will give me 0 right here. Okay. So when I do that, I will have 1, negative 2, 1, 0, 0, 1, negative 4, 4, 0, 0, and then I should do negative 1 minus negative 4, which is going to be negative 1 plus 4, which will give me 3. And then I should do 1 minus 4, so 1 minus 4, which will give me negative 3. What does this row tell you? This row tells you that 0x1 plus 0x2 plus 3x3 equals negative 3. So therefore, x3 equals negative 3 divided by 3, which is negative 1. Okay? So before I even did that, I can still finish changing my matrix. And here I can do R3, replace R3 with 1 over 3 R3. So when I do that, I'll get 1, negative 2, 1, 0, 0, 1, negative 4, 4, 0, 0, 1, negative 1. Okay. And now what I can do, so I have this, everything below this is a 0, that's good. I have this as 1, everything below this is a 0, that's good. And now the only number that's not a 0 in this row is this 1. So I should make everything above the 1 a 0. So I should make this 4 a 0, and then I should make this 1 a 0. How do I do that? Well, I'll take row 2 and I will replace it with row 2 minus row 3. And when I do that, these ones will stay the same because I have zeros here. The only one that'll change is this negative 4. It's important that you follow the steps that I followed, where you choose this and then you make these 0, and then you choose this and then you make the one below it a 0, and then you choose the 1 and then you make the ones above it a 0. It's important that you do that because it will give you the specific structure for the matrix that will give you the solution. For example, let's follow through here. So I have 1, negative 2, 1, 0. And then I will have row 2 minus row 3. So what's 0 minus 0 is just 0. 1 minus 0 is just 1. And instead of doing minus row 3, because then I will have negative 4 minus 1, which will give me negative 5. What I want to do is I want to subtract or add something so that I get 0. So I should do negative 4 plus 4 equals 5, right? So actually, I shouldn't do row 2 minus row 3. I should do row 2, so this will be minus 4 plus 4 times 1, which I have here. So I should do row 2 plus 4 row 3. Because when I do this, I will have there negative 4 plus 4 times 1, which will give me 0. And that's what I want. So when I do this here, I get negative 4 plus 4 times 1, which is 0. And then here I'll have 4 plus 4 times negative 1, which will also give me 0. Okay, and row 3 stays the same, 0, 0, 1, negative 1. Okay, so now I have this 1, and I have below it is zeros, and then I have this 1, I need to make, or I'm sorry, I have this 1 and I have below it a 0. Well, I need to make, and then I need to get this to be a 1, and then above it is a 0. And now what I need is I need this one to be a 0, and I need this one to be a 0. So pause the video and see if you can do an elementary row operation to make this negative 2 a 0. How would I do that? I need to multiply this one of these rows by something, and then I need to add it to row 1 so that I can make this a 0. So you should pause the video and see if you can do it yourself. And then when you unpause it, you will see this. So let's replace row 1 with, I need -2 to be a 0. So -2, and I need to add something times 1. So -2 plus something times 1 equals 0. And the answer is 2. So I should do row 1 plus 2 times row 2. Okay. So when I do that, well, let me do something else too. When I do that, the only thing that will change is this will become a 0. So I will do row 1 plus 2 times row 2. So this one will become 0. Okay. And then I just need this one to be a 0. So if I look here, if I just subtract row 3 from this, these ones will stay the same because I have zeros here. So I can do row 1, replace it with row 1 minus row 3. And when I do both of these elementary row operations, I will get 1, 0, 0, 1, 0, 1, 0, 0, and then 0, 0, 1, -1. So what does this tell you? It tells you that x1 plus 0x2 plus 0x3 equals 1. x2, so 0x1 plus x2 plus 0x3 equals 0, so that means x2 equals 0. And then here, x3 equals -1. So what does that tell you? That tells you that if you can change the matrix to look like this, then this will be your solution. Okay? So this is the solution. And actually, if we take this solution and we come here and we plug it in here, then each equation will be correct. For example, I have x equals 1, x1 equals 1, x2 equals 0, x3 equals -1. So let's take the first equation, x1 equals 1, minus 2 times x2, which is 0, plus x3, which is -1. Does this equal 0? And the answer is yes. So now let me take the second equation, and I will have 2 times x2, which is 0, minus 8 times x3, which is -1, will give me 8. So this equation is correct. And then I just do the same thing for my third equation. 5x1, x1 is 1, minus 5x3, x3 is -1, will give me 5 plus 5, which equals 10. And we see that the third equation is correct as well. Okay, so this is a solution to this system of linear equations here. Okay, and how did we find it? We used elementary row operations. Okay, now if you didn't understand why did we use this first, and then we did this, and then we did this, and then we did this, with more practice, you will see why we did that. But the idea was, and in the next video especially, I'm going to tell you the rules that will tell you exactly which one to do first, which one to do second, which one to do third. Okay? But you already have an idea, because we started with, we have to make the first row, first column, we have to make it a 1. And then everything below that, we have to make it a 0. And then we choose the first number in the second column, and that needs to be a 1. and then everything below that needs to be a 0. And then we choose the first number that's not a 0 in the third column, and then that needs to be a 1. And then we need to make everything above that a 0, so we need to make this one a 0, and then this one a 0. And then we come back, and here we make the one above this one a 0 as well. And when we do that, whatever is left here will give us the solution. Okay? But not all matrices, not all systems of linear equations, you can make it look like this. We will see different examples. In this example, we had one solution. Some examples will give you 0 solutions, and some examples will give you infinitely many solutions. Okay? I'll explain how to use this method to find solutions of systems of equations no matter what they look like. Okay? Okay, but what you should do now is you should do this example yourself. You should do this example yourself at home, and then I will go over this example in the next video. So we have x2 minus 4x3 equals 8. We have 2x1 minus 3x2 plus 2x3 equals 1. And we have 4x1 minus 8x2 plus 12x3 equals 1. You should do this example yourself, and I will go over it in the warm-up for the next video. And the homework for this section, which you can start, is section 1.1, numbers 2, 3, 11, 14, and 15. And this will be due on Tuesday, the 22nd of September. And please contact me on Teams if you didn't understand any of this, or if you want me to go over an example with you one-on-one. Just contact me on Teams, and we will make an appointment to do it by video, or we will do it by chat if that answers your question, if it's easy enough. Thank you.